Hello, in this video we're going to continue talking about convergence tests for series. So the first test that we're going to talk about is the alternating series test. Suppose AN is a sequence that is decreasing and converges to 0. So a sequence of non-negative real numbers that converges to 0 and it's decreasing. Since it is decreasing to 0, it must be everything in the sequence must be non-negative. Then the series of alternating sums converges. Okay, so let's prove this one. In order to prove this one, we are going to show that the partial sums are going to be Cauchy. So if you recall, we showed that a sequence converges if and only if it is Cauchy. In order to show a series converges, we will have to show its partial sums converge. And as a consequence, we got the Cauchy criterion for convergence, Cauchy convergence criterion. So by the Cauchy convergence criterion for series, we need to show this. We need to show for every epsilon positive, there is a capital N in N such that for every N and M greater than or equal to N, we have the partial sum from, so let me specify that M and N are integers. If that is the case, then the partial sum from AN, so from AN would be negative 1 to the power of N AN all the way to, or it starts from M because M is smaller, to negative 1 to the power of N AN is less than epsilon. So this is what we need to show. Now we're going to work on this absolute value, and we're gonna get rid of the absolute value, and then we're gonna show that it can be made less than epsilon. So if you look at the absolute value of negative 1 to the power of M, AM plus negative 1 to the power of M plus 1, AM plus 1 plus etc. negative 1 to the power of N, AN. I'm going to divide off everything by negative 1 to the power of M. So that gives me absolute value of AM minus AM plus 1 plus AM plus 2 minus all the way to the last one becomes negative 1 to the power of N minus M AN. So this sum is either going to be positive or negative. The last term is either going to be positive or negative. So let's look at the sum, and there are two cases. So if you look at AM minus AM plus 1 plus AM plus 2 minus AM plus 3 plus etc. Let's assume that the last term is plus AN. This is going to be, we can combine these in 2 by 2. So we get AM minus AM plus 1. And then we get AM plus 2 minus AM plus 3. All the way to the last one that they are going to be combined with each other are going to be AN plus 2, or I guess minus 2, AN minus 1. These are going to be the pair plus AN. Now, each of these is greater than or equal to 0. Why? Because the sequence is decreasing. So that's greater than or equal to AN since the sequence is decreasing. And if you consider that in a different way, so this is actually AN, which is positive. So if you look at these pairings in a different way, then this is what you're going to get. So if you look at the same thing, AM minus plus 1 plus AM plus 2 minus AM plus 3 plus minus all the way to AN minus 2 minus AN minus 1 plus AN. We can pair them up in a slightly different way. We can pair them up this way, this, and then this one, and then so on. So the pairing that we're going to do is we're going to leave out the first one and we're going to pair them this way. This one with the previous one. So we're going to get this. AM plus minus AM plus 1 plus AM plus 2. Now notice that minus AM plus 1 plus AM minus AM plus 2 is negative, is less than or equal to 0. And then minus AM plus 3 plus AM plus 4 all the way to minus AN minus 1 plus AN. And this is less than or equal to AM for the same reason. Now, there's two cases as we discussed. The first case was if the last term here is positive. This negative 1 to the power of n minus m is positive. Now, also, so let me actually be a bit more specific here, which case I'm looking at here. The case I'm looking at here is when n minus m is even. If n minus m is even, the sum inside the absolute value above is, so this is what we get. We get the last term is a positive an, and we get this argument that we have. So therefore, let me summarize this. Therefore, in this case, absolute value of negative 1 to the power of m am all the way to negative 1 to the power of n an is going to be so we know that it is more than 0, therefore it is positive. So, and then we know that this guy is less than am. So this would be less than or equal to am. In this case, it's less than or equal to am. So also, if n minus m is odd, then the quantity that I had is going to be am minus n plus 1 plus am plus 2 minus am plus 3 plus minus the last term is going to be in fact negative. So an minus 1 minus an. And here I started from am and I'm going up to get to an. So the last term, if you recall, it was negative 1 to the power of n minus m. Negative 1 to the power of m minus m is going to be negative, so I can just write it down as negative. Now I'm going to pair it up in the exact same format. This is going to be am minus am plus 1, am plus 2 minus am plus 3, all the way to an minus 1 minus an. This is going to be greater than or equal to 0, again, since the given sequence is decreasing. So the sequence is decreasing. Therefore, since the sequence is decreasing, the pairs that I have are all greater than or equal to 0. Each one of these pairs, each one of these differences are greater than or equal to 0, which means the whole thing is greater than or equal to 0. Now we're going to pair it up in a different way. So it's a very similar argument. If you write it down like this, am minus am plus 1 plus am plus 2 minus am plus 3 plus am plus 4, etc. minus plus, we get plus an minus 1 and then minus an. Pair it up this way. This is less than or equal to 0. This is less than or equal to 0. This is less than or equal to 0, and finally this is less than or equal to 0. So this becomes less than or equal to am. Therefore, in both cases, again we get the same thing. Negative 1 to the power of m am all the way to negative 1 to the power of n an is less than or equal to am. Okay, so now we can show that it in fact is satisfying the Cauchy convergence criteria. So since limit of a k as k approaches infinity is 0, there is some so did I start with epsilon positive? So let me start here and say let epsilon be positive, just to be a bit more clear. So let epsilon be positive. Since ak approaches 0 as k goes to infinity, there is some integer n such that for every k greater than or equal to for every integer k greater than or equal to n, am is going to be less than epsilon, since am approaches 0. So now, I'm sorry, ak. Suppose n greater than or equal to m greater than or equal to this n. So this means the difference between -1 to the power of m am, the difference of the two partial sums, which would be this sum, which is less than or equal to am, is in fact less than epsilon. Thus, by the Cauchy convergence criterion for sequences, the given alternating I'm sorry, for a series, not sequences. The given alternating series converges. So that completes the proof. Okay. So it seems to be like a little bit of a long proof, but if you think about this, what we did was we found out that the absolute value can be approximated by the first term. We showed that the absolute value of the difference of two partial sums is less than the first term, and since the terms of the sequence approach 0, that the difference of two partial sums also can be made small. Okay, so let's look at that in an with an example here. Look at like an application of that in an example. So if you look at this series from 1 to infinity, -1 to the power of n root n, this converges. So take an equals 1 over root n. So this 1 over root n converges to 0, and this is because square root of x is continuous and 1 over n approaches 0. And also 1 over root n is greater than 1 over root n plus 1. Since root n is less than root n plus 1, since n is less than n plus 1 and root x is strictly increasing. So we have to check these two conditions. The sequence approaches 0 and the sequence is decreasing. So by the alternating series test, the sum of -1 to the power of n over root n converges. And that's exactly what we wanted to show. We wanted to show this series converges. Okay. So let's move on to, so again, you have to prove these two things. The series, series is alternating. You have to make sure that the series is alternating, and those ANs converge to 0 and they're decreasing. So those two things must be checked. Okay, next we're going to talk about the absolute convergence test. Suppose AN is a sequence for which the sum of absolute values of AN converges, then so does sum of AN. Okay, so let's look at the strategy for proving this theorem. One might think that it might be a good idea to use the comparison test. Why? Because absolute value of an is larger than an. So comparison test tells us that if the larger series converges, then the smaller series also converges. However, there's a problem with this. There's an issue with this argument. And the issue is comparison test only applies when the sequences are, the terms are non-negative. Here, the problem is an could be negative. And that's exactly what the problem is. So how do we deal with that? Well, one thing we could do is we could look at an plus absolute value of an. This is always greater than or equal to 0. So it's either 0. If an is negative, that's just 0. If an is positive, it would be twice an, which is also positive. So in any case, this is going to be positive. And furthermore, an plus absolute value of an is less than or equal to twice absolute value of an, which we already know it converges. So we are going to go ahead and use that strategy. So an plus absolute value of an is equal to twice absolute value of an if an is greater than or equal to 0, and it's 0 if an is negative. Thus, an plus absolute value of an, first of all, is always greater than or equal to 0, and second, it is less than or equal to twice absolute value of an. Now, note that by linearity for series, the series twice absolute value of an converges, because we know if a series converges, then if you double each term, you also get a convergent series. So now we can apply the comparison test. By the comparison test, the series sum of an plus absolute value of an converges. N equals 0 to infinity. Okay. So we got that this converges, but how do we extract an from there? Well, it's actually not that difficult. We could just subtract absolute value of an from that. Now, by linearity, property of a series, sum of an plus absolute value of an minus absolute value of an converges. So we are taking the linear combination of two series. One of them is an plus absolute value of an, the other one is absolute value of an, which means sum of an also converges. And that's exactly what we wanted to prove. So if sum of absolute value of an converges, then sum of an also converges. Okay. So let's do an example on this. Prove that the sum of cosine of n over n squared is convergent. Okay, so this might seem in the beginning that maybe this is like an alternating series, but the problem is cosine of n is a function that doesn't really behave very well in terms of being positive or negative. It could be, if you look at the graph of cosine, you see like it doesn't really alternate. It goes from positive, and negative, so it's not quite there's no like a pattern in there. So we can't really use the alternating series test, but we can take its absolute value and compare it. Let's do that. So if you look at cosine of n over n squared, this is less than or equal to 1 over n squared. Now, I know 1 over n squared converges. I know that sum converges because, so if I look at this converges. because it is a P series with P equals 2 and P is more than 1. So this converges. By the comparison test, the sum of absolute value of cosine of n over n squared converges. Now, since I'm using the convergence test, I will have to make sure that both sequences are non-negative, and that's why I put a greater than or equal to 0 in the beginning here. And when we do that, we realize that this converges. Thus, by the absolute, so the test that we just proved, it's called the absolute convergence test. So by the absolute convergence test, the series cosine of n over n squared converges. And that's exactly what we wanted to prove. We wanted to prove that the series cosine n over n squared is convergent. Okay, so finally one definition, and then next time we'll talk more about tests for convergence for series. A series, a sum of an is called absolutely convergent if sum of absolute value of an converges. If sum of absolute value of an converges, but sum of an converges, but sum of absolute value of an diverges, we say the series is conditionally convergent. Let me give you an example. So if you look at this sum of negative 1 to the power of n over root n, or over root n. We know this converges. We just proved this. But if you look at the sum of absolute values, we get sum of 1 over root n. This one diverges because if you look at the series, it is a P series, and P is 1/2. Which is less than 1. So that diverges, but the series itself converges. So we say the series, the sum of negative 1 to the power of n over root n, converges not absolutely, but conditionally. So this is a good example to keep in mind. Okay, so that brings me to the end of this video. So we will discuss more on convergence tests for series in the next video. So I will see you in the next video.